Okay, so let's continue with more applications of the pigeonhole principle. Well, let's just say last lecture. Last lecture we saw the theorem, which attributed to Ramsey in a much more general setting. And let me just remind you what the theorem says. It says that okay, maybe let's just implement a notation that I've used in the past. I used it earlier today to solve a question that one of you had in the problem set. If you have a set like the natural numbers, and you have a small number on these square brackets, then this is the subsets of the set in the square brackets that have that size, right? So in this case, this will be the set of all pairs, all sets that have exactly 2 elements, right? And the way I stated this this theorem is that if you have a bunch of people, at least 6, but we can write it in more general idea. Let's say, let's just write it like this: if n is at least 6, we should first, if n is at least 6, any party of 6, and then you take all possible relations and you divide them into 2 types, right? Is split into 2 colors, right? So some of these elements are in one, some of the other elements are in the other. So friends and no friends. Then three elements of n satisfy. There's a better way of writing this, right? There is 3 elements, let's call them P, that are inside of this party, and they have size 3, such that all the relations between them, all the pairs between them, so P to the 2 is the same color, right? And remember, we proved this directly using the pigeonhole principle. So let me maybe rewrite just the example so that you know what I'm talking about. So this is n, and then some of these are red and all the others are blue, right? We split this into 2 groups. Am I missing anything? I'm missing this one, right? Right? So here, by split, we're saying all of the pairs of elements are being split into A. And okay, maybe how about R for red and blue, right? And there's a triangle right here. So if you consider these 3, then P, if P is the set, maybe I should use a different color, right? So there are 3 elements, these ones, and if you look at all the pairs, that forms a blue triangle, right? So this would be P in the example. And notice that indeed it is true that all the pairs of P are all blue, are all of the same color. So why don't we spend just a little bit of time trying to generalize this idea? How would you generalize this? And I will not necessarily prove the more general version of this, but it's the same idea that we already covered last time, and hopefully we can include some interesting examples of how this can be applied. What if instead of finding 3 people with the same property, you want to find a larger group? Would that be possible? Because right here, I'm saying no matter how you organize 6 people or more in a party, you can always find 3 with the same mutual relation among themselves. But can we find more? Can we find 4? Maybe not in a party of 6, but maybe in a larger party. So this is a theorem slash definition. Let's write it this way. And this is the definition of the Ramsey number. Ramsey number. And of course, the theorem says that the Ramsey number exists and is well defined. Let me see the chat for questions. Okay, great. So R k is the least integer such that the party problem is satisfied in the sense that any any two coloring of this set RK, the couples, right? We could obviously also think about increasing the number 2 to more colors, and I'll tell you how to do that in a second. But the harder question is how do we increase the size, right? Right. Any true coloring produces a set P, which is inside this party. You can find how many K people inside this party, such that if you take all the pairs in P, same color, right? Or let's say R, are all the same color. So for example, we just calculated R of 3 because K is the question. We're trying to find 3. So the question is, how many do we need to invite to guarantee 3? It also makes sense for 2. Maybe we can try to answer some more of these questions, right? How do we compute these numbers is a very interesting question. What do you think would be the answer for 2? So R of 2 is the least integer such that any coloring of whatever that number is, if you color the pairs into 2 pieces, you can find a subset P of size 2, all of whose pairs are the same color. So what do you think would answer that? If we want to be more specific, is what number of dots do I need to draw on the plane so that no matter what configuration of colors I use to connect all of these, there will be K elements such that if I connect all those K, I can do so with just using the same color, right? Actually, I drew 6 again, so maybe that's not a very interesting example. What do you think should be the case for R of 2? And you should also tell me what the answer is for R of 3 because we proved this already. That's the first theorem that we proved. So R of 2 is easy, right? It's saying when K is 2, the set P that we want to find has size 2. So we want to find 2 people. We want to find 2 people that have the same relation. But that's kind of obvious, no? Because 2 people will always have the same mutual relation among each other. Either they're friends or they're not, but there's only one edge to consider, and that edge will always have the same color as itself. So K equals 2 is kind of trivial. You only need to invite 2 people. 2 people already have the property. They're either friends or they're not. So this is completely uninteresting for K equals 2. K equals 3 is asking the question, there are 3 people that I want to guarantee will have the same mutual relation among each other. How many people do I need to invite? Well, Ramsey's theorem says it's 6, right? Fewer than 6, namely 5, doesn't work. I gave you that example last lecture. I can maybe look it up right here somewhere. Where is it? Where is it? Down here. This is the example where 5 people are not enough. So the least integer is not 5. It has to be 6 because with 5 it doesn't work. Here there are 5 people, none of which how do I say this? None of whose subsets of size 3 form a triangle of the same color, right? There are no red triangles and there are no blue triangles there. Okay. So what about 4? How do we figure out the number for 4? If you want to guarantee that there will be 4 people with the same mutual relation, maybe it's not hard to see that 6 is not enough, right? You probably need something much larger, like 12. Okay, that's a really good guess. The least number is actually 18. 18 is the least number of people you need to invite to guarantee that 4 will always have the same mutual relation regardless of how they are organized. What about 5 and 6? You might feel like you're spotting a pattern here. And if you haven't heard about this, this might surprise you. But 5 and 6 are actually unknown. So these are already open problems. 43 is a really good guess. 43 is enough. It's an upper bound for 5. But the least number is still unknown. At least it was a few weeks ago. Haven't checked. So starting from 5, this is already completely unknown. Oh, really? Just random guessing. That's crazy because 43 is actually really close to the real number. It is known that R5 is, I think there's only 5 possibilities. It's either 43, 44, 45, or something like that. But it's very, very close to that number. The exact number is unknown. And Erdős, who worked in this area for a while, famously once said, he tried to explain with an analogy why these numbers are so difficult to compute. He said, if an alien race came to enslave the Earth, yeah, no, it's a really good guess, 43. If an alien race came to enslave the Earth and they said, we will set you free and forgive you and forgive your life, basically let you go free with no harm, if you tell me what R of 5 is, then humanity should put all of its efforts, all computer scientists, all mathematicians, to work on finding R of 5 and a proof that that is R5, and then we would present this to the alien overlords and gain our freedom back. But Erdős said, if instead they ask for R6, then we should devote all of our attention and all of our resources to building nuclear weapons, because it will be way easier to try to fight off the aliens than to find R6. There's no hope of ever finding R6, which is not necessarily true. Maybe someone just needs a really clever idea to see this. And this is an active field of research. Better bounds were found not too long ago, and similar questions like this have been answered just this year or even last year, right? So this is a very, very recent and active field of research, even though these questions are, almost 100 years old by now, right? So if you're interested, this is one thing you can consider doing research in. No one knows what R5 is, R6, and for bigger numbers, it just gets a lot more complicated. It might not initially be obvious to you why this is so difficult. Like, why can't you just have a cluster of computers finding all possible combinations and then saying, well, if we only have 5 possibilities for R5, why don't we just rule out all of the ones by elimination or something? That is impossible, right? Because there's just too many possible ways of doing this. You should know how to calculate how many possible ways there are, how many graphs there are, how many ways can you combine red and blue to make a valid configuration of these things. But anyway, something that is surprisingly not that challenging to prove is the fact that all of these numbers exist and are finite. Even though it's impossible to calculate what those numbers are, I could maybe we won't have time for this, but there's a very short argument, and the idea is not much deeper than the one we already gave before, that tells you why all of these numbers must exist. R of 1 billion must exist and must be a finite number, even if it's unfathomably large and impossible to pinpoint what that number is. And yeah, so that is something worth thinking about. Even more so, there's something that maybe doesn't make too much sense anymore because these aren't integers. So this, I'm going to put this in quotation marks just because the idea is obviously clear, even if it isn't properly defined the way I wrote it up here. This works for any natural number. Of course, finding a general formula for Rn would be way, way stronger. Like, this would be a huge achievement. Unlikely to be, I don't know if maybe someone even proved that this is impossible because of how rapidly these numbers grow. I have no idea. I don't think anyone knows if this is possible or not. For some other functions, it's known that it's impossible, right, to find a closed formula. Anyway, putting this in quotation marks, if you put aleph 0 here, I know this is not an integer. I know the definition up here doesn't make sense. But you could make it make sense, right? Instead of saying integer, just write cardinal and then it makes sense. I think that's the only thing you have to change. You can actually prove that this is aleph 0 itself. So r of infinity is infinity. And for other infinite cardinals, it is funny that this is actually not that difficult to calculate. When things become infinite, it becomes way simpler in some sense, which is counterintuitive. So this is known as the infinite Ramsey theorem. And if you know how to prove the infinite Ramsey theorem, which I could tell you how, but it's a bit, I mean, with the chapter we saw on infinity, we have all we need to write this proof. It's not that difficult, but it takes a bit more time than I want to spend on this. If you know this, then you can prove all of the ones, all of the smaller ones, right? You can prove the smaller ones independently, of course, and that would probably give you a better idea of what is going on. But if you know the infinite one, that is somehow stronger than the ones before. And these arrows, these implications, carry the flavor or can be directly proved by something that we only had very short time to actually study, but we did mention, and this is called compactness. Now, why this is compactness, of course, would take me a long time to explain, but just know that the idea that we saw about compactness is the same idea. And in fact, if you pick an appropriate topological space, then this is just a fact of sets being compact, that you can prove all of these numbers by knowing the infinite case. And I think I did mention compactness is a means by which you obtain a finite result, knowing that something infinite is true. So it is perhaps unsurprising that all these ideas are connected. Okay, and someone asked in the chat, in that case, the only thing we can conclude is that there are such numbers for every natural number. Yes, there's no way of knowing what that number is, but we can prove that these numbers all exist. And we can even do a little better than just knowing that they exist. Using compactness, all we know is they exist. But if we prove them directly, there is a way to show that these are bounded by something. And I would have to brush up my memory on this. I think there's one bound, actually, I just answered my own question earlier. One bound that is known is that this is just a power of n twos, I believe. Maybe you need to add an n somewhere here, but that is one way to bound this number. So we do know a large enough size of a party. We just don't know what the least size of a party is. And I think using this bound, that means that there must be a formula for at least it's computationally possible to write down symbols that give you a formula. But don't quote me on this. I have to double check. And this is, by the way, not the best known bound. There is this researcher called David Conlon, and I think he currently owns the research to the best known bounds for this, and they are way better than the one I just wrote down. Sorry, is it David? Why am I blanking on the name? Anyway, he lives in California somewhere. What was I saying? Right. And what does the infinite Ramsey theorem say? So this theorem, if you want to write it down specifically, it says that for any, splitting or two coloring, you take this set and color it in two colors. You have to take the natural numbers, right? You have to take an infinite set. You take all the pairs. There is a set of size aleph naught, but if I want to write this a bit better, there is an infinite set. An infinite set A, all of whose pairs are the same color. And that is just very surprising, right? Think about this. You have infinitely many people, and these are spread using all sorts of weird relations. All of these possible combinations. There are, by the way more than countably many possible combinations of this, right? Way more. And the theorem says that you can select some infinite set a set that has the same size as the original one, such that every possible line that combines these are all the same color. So basically all red in the example that I wrote here, regardless of whether how much blue you used to color the original set. Isn't this weird? I find this very surprising. Now, there's more that can be said about this. What if we increase the number of colors? Instead of 2, what if I use 10? Or what if I use infinitely many colors? There's so many variations of this. Like I said, it's a very active field of research. It is actually part of my own research. So if you're interested in talking more about this, then I'd be happy to. But I think this is a good enough place to stop. This theorem can be used, the last one I wrote, to prove the Bolzano-Weierstrass theorem from real analysis. So this is actually, intimately connected to many other fields. It is not just something about combinatorics and lines and edges and points and pairs. This is connected to measure theory, to analysis, to topology, to many other things. Okay, so we have some time left, and instead of just continue to ramble, okay, let me see. Okay, yeah, questions in the chat. So, do spend some time thinking about the quiz. If you have questions about the final or your grades or the problem sets or anything, I will stay here until the end of the lecture. And let me pause the recording for now.